Okay, all right. So, class, we are in section 6.3, and I want to point out a few more theorems to you from section 6.3. The one that I should point out here, there's several, but one of them is called the best approximation theorem, which is theorem 9. But you really probably already understand this better than you think. But the idea is that if you have a subspace and you have any vector in the subspace and you project, you have an orthogonal projection of that vector y onto subspace W, then the y hat vector, which is, again, that's the orthogonal projection of the vector y onto W, that would be the closest point in that subspace W to y. It would be closer than any other vectors in the subspace, any other vectors V in the subspace W, different from y hat. So that, and intuitively, it makes sense. You've seen it with like a previous example, but I just wanted to make you aware. Formally, that's called the best approximation theorem. I know in the multiple choice exercises they sometimes reference theorems and things, and you should just be aware of that. And then hold on here, is it showing up? Okay, good. And then also another thing too that we touched upon in the last class was orthonormal vectors. So orthonormal vectors are vectors that are orthogonal, but they also have unit length. And one nice thing about orthonormal vectors is if you have an like theorem 10, this theorem 10, okay, here, kind of highlight it there a little bit. This theorem 10, if you have an orthonormal basis, okay, and again, if you have an orthogonal basis, you can make it an orthonormal basis just by scaling the vectors appropriately so they each have length 1. And you know that the projection of a vector y onto a subspace W is given by this formula, but the denominators, okay, maybe I'll, like if you look at this, kind of want to highlight what's important, most important. If you look at like y dot u1, okay, that is, like normally below it we would see u1 dot u1, right? And y dot u2, normally in the denominator we would see u2 dot u2. But instead the denominators are 1s, right? They have to be 1s. So why is that? Why is like for y dot u1, where did the u1 dot u1 go below in the denominator? Why is it equal to 1? That's right, Matthew. It's an orthonormal basis. And so if you take u1 dot u1, you will get 1. If you take u2 dot u2, take the dot product, you're going to get 1. Okay, and the vectors have length 1, and that's exactly right. That's exactly right. Noah says the vectors have length 1, and if you dot product a vector with length 1 with itself, you're going to get a 1. Okay, that's right. And so it's kind of that's kind of cool. But then also look at how you can write the projection of y onto W. You can, if the matrix U is defined to be the matrix whose columns are these orthonormal vectors, then the projection of y onto W can be written as U times U transpose times the vector y. Okay, and to convince yourself of that, you can make up a little example so you could see that that's true. I don't necessarily want to go through the proof here, but it is true. So theorem 10 was another theorem that you should be aware of, and I wanted to do one. I mean, are there any questions on that before we move on? All right, all right. Well, all right, very good, very good. Well, what I'd like to do is I'd like to do another example with you. Now, this is my example. I made this one up. Okay, and I'm trying to think of examples that will intuitively help you feel comfortable with these orthogonal projections. So, here's the example. I didn't have a chance to type it up, but here it is. Let me give you a moment to copy the example down, okay? And then we'll go over it. Okay, this question here maybe. V2 is -2, 2, 0. Hold on. Yeah, -2, 2, 0. Let me see here. So this is, okay, very good, very good. Okay, so in this problem, we have a vector y. Hold on, got to get it on blue here. Okay, we have a vector y, and we want to find the distance in part A. We want to find the distance between this vector y and the plane in our cube spanned by the E1, E2 vectors, also known as I and J vectors. And then in part B, we want to find the distance between the vector y and the plane in R3 spanned by vectors v1 and v2. Okay, so let's go ahead and try to work through the problem here. I'll go to the next. I assume everybody has it copied. Okay, so let me go to the next page here. Again, what helps me tremendously is a picture. A picture. Oh, okay, Christy. I guess I didn't ask. Is everybody okay? Hold on. I didn't ask yet. All right, all right. Yes, Matthew, I had answered that. The vector v2 is -2, 2, 0. That's not a 12. That second entry is not, that's not a 12. I know, it looks like there was a 1 there. I erased the 1 and put a 2, but good question. I want to make sure everything's clear. No problem. All right, so let's start off by drawing a picture. Okay. Okay, so until you're, I mean, you don't want to just be, sort of robotically applying formulas. You want to understand the geometry behind what's going on. And so what I'm doing is, hey, I'm drawing a vector E1 and E1 and E2. Now this should be an E2. This is an E2 here. E2. Okay, I have vectors E1 and E2 drawn, and they are in a plane, actually the XY plane, right? W here is the span of E1 and E2, and I've drawn the point 235 outside of the plane W because the vector 235, the coordinate 235, is not in that plane. It's not in that plane. And to find the distance between this plane W and the point 235, well, the distance is going to be the length of this vector that's perpendicular to the plane, that goes from the plane to the point 235. So we notice that, I mean, it's easy to see, right, that of course, whoops, hold on. Of course, E1, the set E1, E2 forms an orthogonal basis for this space W1, and I guess I should label this W1. Okay, that's W1 there. And so we know how to find the projection. Well, let me be more clear. In order to find the length, of that's not too neat. Hold on. Yeah, in order to find the length of that red vector, I need to know what this vector is. I need to know what that projection vector is, y hat. Y hat is the projection of the vector y onto subspace W1. If I can find what y hat is, and I know what the vector y is, then I can find this vector, this red vector here. And once I know the red vector, once I know what it is, I can get its length. That length will be the distance. Intuitively, you probably already know the distance that the point 235 is from this plane. But let's confirm it, using our linear algebra. So because you have an orthogonal basis, the coefficients of E1 and E2 may be found using these nice formulas that are true only when you have an orthogonal basis. The dot products I computed, they're not hard, you know, you compute the dot products and you will get this. You'll get the projection of y, vector y onto subspace y1 is equal to 2 times E1 plus 3 times E2, which is 230. 230. Okay, give you a moment to catch up here. Okay, so let me ask you what they're saying here in the problem is that this coordinate here is equal to 2, 3, 0. Right? That's what that coordinate is right here. It's 2, 3, 0. So does this make sense does this make sense that projection would have to be 2, 3, 0? Yeah, I mean, you know, the span of these E1 and E2 vectors is the XY plane. And so if you take a vector out of the plane, the distance from that vector to the plane would just be the Z coordinate, which would be 5. But the point is, if you go from 2, 3, 5, just drop it down, perpendicular down, you would be at 2, 3, 0. Okay, what do we do to confirm our distance mathematically? Well, all we need to do is, well, if you take the difference between the vector y and the vector y hat, subtract those vectors, you're going to get 5. So if you take the vector y, and the vector y is 2, 3, 5, and you subtract the vector 2, 3, 0, which is the projection vector, you'll get, I mean y minus y hat is going to equal 0, 0, 5. That's right, Solomon. 0, 0, 5. And so, oh, that's all right. Good questions. Good questions. And so again, I'm using this. This is my little example for you to geometrically get a feel for the situation. Are we okay so far? Are there any questions before we move on to part B? Okay, James is good. Matthew's good. Robin's good. Okay, very good. Thank you, everybody. Well, now part B, we're still going to have the vector y, and we're going to find the distance between y and the plane in our cube spanned by vectors v1 and v2. Now, v1 and v2, what do you notice about the set v1 and v2? What kind of basis is that for the plane that those vectors span? What kind of basis is v1 and v2? Take the dot product of v1 and v2. What do you get? Orthogonal. Oh, so v1 and v2, since v1 dot v2 is 0, the vectors v1 and v2 form an orthogonal basis for the plane that they span together. So, okay, well, we're just going to repeat this process that we did in part A for part B. We're just going to repeat the process. Okay, so you know, I'm going to call W2 now the span of these vectors v1 and v2. Okay, and since v1 and v2 is an orthogonal basis for W2, I can compute the projection of the vector y onto W2 this way, using the same formulas, but using the same process that I used in part A. All right, so let me give you a moment to copy that. And then, you know, I go through the calculations and I get down to here. All right, so I'm going to just let you copy that and let me know if you have any questions. Okay, all right, so now, okay, Matthew, we'll get to that. So now we compute this, and oh my gosh, look, the projection of the vector y onto W2 is 230. 230. That's the same projection as we got in part A. For part A, the basis vectors for the subspace were E1 and E2. Here, we have different basis vectors for subspace, but yet the projection is the same. Why is the projection of the vector y onto W2, why is it equal to the projection of the vector y? Let me rephrase it. Why is the projection of the vector y onto subspace W2, which is equal to the vector 230, why is that projection vector the same as the projection vector of y onto the subspace W1. Why did we get the same projection vectors? I mean, why are they the same? I mean, let me go back here. Here's E1 and E2. And here's V1 and V2. W1 is a subspace spanned by E1 and E2. W2 is a subspace spanned by V1 and V2. Well, but why are the subspaces the same? So I mean, for this to work, for this to be true, what happened, that we got the same projection vector in part B as in part A, it would have to be that the subspace in A is the same as the subspace in B. Well, Robin says they're both planes of R cubed. Okay, they're both planes, yeah. What axes go through the plane in A? What axes go through the plane in A? If you were to draw the plane in part A, what axes go through that plane? X1 and X2. That's right, Solomon. Or, you know, X and Y. Part B, those vectors, what axes go through the plane in part B? Let me rephrase it. Let me rephrase it, okay? Let me rephrase it. In part A, you have vectors E1 and E2. They span a plane. Now, the plane that they span, let's think in terms of kind of, in three-dimensional space, you have three planes. You have the XY plane, you have the XZ plane, and you have the YZ plane, right? You have three planes. Okay, in three dimensions. I mean, let's just consider these three planes in three-dimensional space. Okay, so we know what they look like. So for A, the span of the vectors E1 and E2 is a plane. Which plane is the span of E1 and E2? Is it choice 1, choice 2, or choice 3? It's the XY plane. But what is the span? So this is okay. I'm glad I'm doing this problem because we're getting lots of good questions. The span of two vectors is any linear combination of those vectors, right? It's the set of all linear combinations of the vectors. So the span of two vectors in R3 forms a plane. In this case, for part A, the span of the vectors E1 and E2, that plane would geometrically be the XY plane. That would geometrically have to be the XY plane, because what's the third coordinate equal to in both vectors? 0. There's no way the span of those two vectors is going to go up or down. The plane isn't going to be, it's going to be a flat horizontal plane. Okay. Now look at the vectors V1 and V2 in part B. Tell me about the third coordinates. The third coordinates are 0. So the span of those two vectors, it's a two-dimensional subspace, it's a plane, right? There are two vectors in the basis, two-dimensional subspace. It has to be a plane and it's the XY plane. So the vector Y in parts A and B, even though the basis vectors are different for A and B, the span of those vectors in A and B those basis vectors are the same plane. And that's why you're getting the same projection vector in part B. It's not an accident. It's not a coincidence. You know, we don't see too many coincidences in linear algebra. You know, but W1 equals W2. I'm just saying that the subspaces are the same. The planes are the same in part A and part B. And so the distance from the vector y to W2 is also 5. Okay, how many found this example helpful? Is this helpful geometrically for you, to help intuitively, to help you have a feeling for? Okay, wonderful, Matthew. Thank you. And thank you, Max. Thank you, Solomon. Thank you, Christy. All right, well, now I have a question for you. I got one. I want to go to the next page, but may I go to the next page? Are we? All right, let me ask you this. Would the distance from the vector y to the subspace W3, which is the span of the two vectors in R3, so it's a, what geometrically, what is W3 in R3? The subspace W3 would be a what in R3 geometrically? W3 would be a the span of any two linearly independent vectors in R3 geometrically is a forms a, well, in A, what was this, what did the span of those two vectors look like? A plane, right? In B, you had a plane. Same here. The span, that's right, Matthew, the span of these two vectors is a plane. It's a plane in R3. This is a plane. This is a plane in R3, right? Okay, one moment. So I'm wondering, well, gee, it's a plane too. This is a plane. Would the distance from the vector y to this subspace W3 also be 5? Well, I can tell you the answer is going to be yes or no. Solomon thinks definitely not. Well, okay, so, all right, that's right. This plane, this here, this plane W3, would the span of those two vectors be the XY plane? Definitely not. Definitely not. It'll be some other plane. So the projection can't be the same. So the answer's going to be, I want to be a little bit careful about this. It's going to be no. It's going to be no. I'm just thinking, is it possible maybe just by luck it could be 5? Let's see. No, I don't think so, because any other plane is going to have a different orientation to it. We got to be a little, let me think here, hold on. I think it, well, let's just say no, okay? I mean, but but you see what I'm trying to get at, right? I'm trying to help you think intuitively. So it'll be no. It'll be no. All right. Are there any questions on this little example? Okay. Any questions at all? Let me ask you this. All right. Let me stop the recording. I think we're good.